Okay, so the first presenters we have is from a group called the BPMI Valve Cycling Rig, with the advisor as Dr. Allison. So I am going to ask that the first student to present, make sure that when you're presenting that you have your camera active, but only the camera active of the person who is presenting. And then when you're done presenting, you turn off your camera for the next person to turn on their camera as you guys go through your team for the presentations. And do not forget to introduce yourselves as you start presenting. So if the first person that's going to start presenting, go ahead and activate your camera. You can start your presentation now.
All right, thanks, Dr. Barty. Good evening. My name is Mark Dillon, and I am the team leader for the BPMI Senior Design Team. Our team was tasked with designing and building a valve cycling rig. The rig is to be used to test a valve for up to 10,000 cycles. A cycle is defined as a complete open and close of the valve. In addition, the rig was to have the ability to record the torque required to open and close the valve over time. Adjustability in height and valve size was also important to the design of the rig due to various valve sizes and heights that will be tested in the BPMI testing facility. Our rig was designed to apply a torque of up to 55 foot-pounds to the valve during the open and close cycle. Now a little bit about our sponsor. BPMI stands for Bechtel Plant Machinery Incorporated. They provided the funds that made this project possible. BPMI is a prime contractor for the U.S. Navy's nuclear propulsion program, which is responsible for nuclear propulsion systems in aircraft carriers and submarines. They have offices in Pittsburgh and New York. One of the first things that our team decided to do was to divide the team into subteams. This allowed a small group to be focused on one part of the project. The three subteams that were created were mechanical, PLC and HMI, and motor actuator. The mechanical team was responsible for the design and construction of the cart. The PLC HMI team was responsible for the digital side of the project, such as writing the programs and displaying information. The motor actuator team was responsible for the motor, gearbox, and actuator which turned the valve. Each of these subteams had a subteam leader which communicated with the team leader about progress and spoke at weekly meetings about progress of the subteam. These subteam leaders were Josh, Daniel, and Chris. Now I'll pass it off to Tim, who will discuss the mechanical side of the project.
Hi, I'm Tim Collins, and I'm a member of the mechanical sub-team. Our job throughout the school year was to design and then build and assemble all the mechanical aspects of our testing rig. Even though we got sent home early due to the COVID-19 pandemic, our team ended up getting the rig fully assembled on the last day we were together. So we spent the whole fall semester designing our rig and figuring out what we can do mechanically to solve the problem at hand. We needed a design that was adjustable to accommodate different valve sizes and heights, portable so that it could be moved to and from a pipeline, and stable so that it supports the weight of the motor and gearbox and the torque load applied during testing. We also needed it to withstand a temperature of 700 degrees Fahrenheit and last throughout a 10,000 cycle test, which we estimated would take multiple days. One of our first tasks was finding a cart to use for our testing rig. A senior design team in 2013 used a heavy-duty industrial cart for a fatigue tester project, and it was available to us if we wanted it. We knew this would be stable and portable, and that we could add components to make it adjustable. We considered buying a vertically adjustable cart, but we decided against it because it would be expensive and may not be as stable. So we stripped off all the old components from 2013 and started adding our modifications. Next slide. One of my main responsibilities was the stage. We needed something to elevate the motor and gearbox from the top of the cart and provide stability during testing. We decided to use 2x2 80/20 for the horizontal and vertical members, and then put corner brackets at each intersection to provide extra support. A 1/2 inch thick, 2 foot by 1 foot aluminum plate was placed on top of the 80/20 assembly and fastened with T-nuts. When this assembly was fastened to the top of the cart, it turned out to be very rigid. Next slide. The stage also plays a key role in the adjustability of our rig. It elevates the gearbox 12.5 inches from the top of the cart, which allows us to meet our height requirement and have room to adjust the shaft vertically through the gearbox output. The T-nuts that go through the plate and anchor into the grooves that run along the top of the 80/20 allow it to slide forward and backward. As you can see in the bottom image, we machined 1.5 inch slots in the plate perpendicular to the 80/20 grooves so that it can move side to side as well. This design allows the operator to align and secure the gearbox and shaft with the center of the valve body. Now I'm going to pass it off to our sub-team leader, Josh Bowder.
Hi, my name is Joshua Bowder, and I'll be talking about the mechanically ensured safety in our rig design. So the first safety concern that we needed to take into account was safely moving the rig to and from testing locations throughout the facility. Our rig, which weighed about 700 pounds with all of the hardware on it, was able to be moved with just 13.5 pounds of force by selecting proper wheels, and also was able to follow OSHA ergonomic recommendations by implementing vertical handles, which allow an individual different heights to be in a sound and secure pose while in movement. Next slide. So the second concern was pinching and entanglement. We, to mitigate this, we encapsulated all of the moving parts and the valve interfaces in a safety cage. The safety cage was designed in line with OSHA standard 1910-212A, which specifies standards such as gaps and spacing that's permitted in industrial guarding. We also implemented labels and warnings according to ANSI standards, and for our own purposes, integrated a fault sensor so that when the sides of the cage were not properly secured and closed, the operation would cease or not be able to start. Next slide. Now, with all of this, we did not want to inhibit function, and so the safety cage was designed to be fully adjustable for the variety of size and shaped valves that were determined by BPMI, as well as the positions that they could be in, anywhere from our ankle up to our waist. The side panels, for ease of adjustment and setup, were one continuous swinging door that would have a latch and a fault sensor so that you could easily tell if it was set up properly or not. Next slide. Now, our design changed slightly from what you just saw, this being our final design on the slide now, to increase both durability and adjustability. So we implemented different brackets, which increased the stability and strength of attaching to the cart itself, as well as made it easier to adjust from the side of the cart instead of having to be in front of it where piping assembly could be. We also implemented mesh retainers, which increased the strength of the sides of the panels, as well as plates that held the hinges in alignment for ease of adjustment as well. Next slide. The final consideration that we took into account was heat. The valve itself could be up to 600 degrees Fahrenheit, and for an operation taking 7 days, all of our equipment, if not properly protected, will get very hot. To mitigate this, we implemented a heat shield on the front of the cart that you can see there with an insulated back that touching hazards for the heat shield would be mitigated, as well as increasing the reflectivity of the heat shield. We implemented cones and chains to mark off the danger areas, which is standard for BPMI, as well as proper warnings on the equipment that would get hot itself, according to ANSI standard. Now I'll pass it off to Susie Jones to continue on our mechanical design.
So I was mostly in charge of the piping mock-up as well as attaching the rig to the pipe. So as you can see pictured here on the slide, we made custom manufactured V-blocks in-house to allow for easy assembly to the front crossbars to firmly attach the rig to the piping assembly without damaging the pipe. The V-block assembly contains an insulation to protect the aluminum rails from the high heat of the valve, an inner V-block with tapped holes to accept screws passing through the clearance holes of the outer V-block, and the outer V-block itself. The V-blocks can accept a range of pipe or fitting sizes with 4 points of contact without crushing what it holds. The V-block assemblies can slide relative to the horizontal T-slot rails, which allows for a range of valve housing sizes. The entire front assembly, composed of the V-block assemblies and the horizontal T-slot, is connected to vertical T-slot rails and can be raised or lowered to accommodate any valve mounting height up to the top of the rig. All of this enables us to securely attach the cart to the piping assembly without fear of damaging the piping or the valve while still maintaining maximum adjustability. In order to test our setup, we would have needed a piping assembly of our own. However, the valve is made to be welded into the piping assembly, and it is a borrowed component. So another task for the mechanical subteam was to create a piping assembly to securely hold the valve without modifying it. as is pictured on the next slide. So our solution is the piping mock-up pictured here. The mock-up mimics BPMI's application conditions, is fully adjustable, and firmly holds the valve, all without modifying the valve or interfering with the V-blocks. It is constructed mostly of standard schedule-forwarded piping and fittings anchored to a large metal plate for stability, and has slip fittings to allow the valve to be raised or lowered to the desired testing height. A custom clamp keeps the valve from rotating about the axis of the horizontal pipe, yet remains out of the way of the V-blocks and is adjustable with slip fittings. The most difficult portion of the design was figuring out how to grip the valve housing firmly without interfering with the rig attachment. We used the expanding plug assembly on the next slide. The expanding plug fits into the valve housing at either end, and as a machine screw threaded into the insert is tightened, the plug expands against and grabs the housing. The back of the plug is standard pipe thread and threads directly into the mock-up fittings so that it interfaces smoothly with both the valve and the rest of the piping mock-up, so it does not interfere with the V-block attachment. And next is Micah to talk about the PLC.
My name is Michael Wenger, and I'm going to introduce the control system of the project. Next slide. The project required the valve to be opened and closed autonomously for possibly many days without an operator being present. Additionally, the control system needed to apply a constant rotational velocity to the valve. It needed to measure, display, and record torque data. And finally, it needed to allow test parameters to be altered. This included rotational speed and pause time. Pictured here, you see where the equipment solutions that we chose, an HMI shown up top, a PLC, and an Aerotech control behind it. As seen on the next slide, users will input commands and view data on the HMI, or human-machine interface. This essentially is an industrial level touchscreen. The next piece of equipment, which is essential to the control system, is called a PLC, or programmable logic controller. The PLC is the primary computer of the control system. It handles requests from the HMI commands and initiates the actions to be completed by the motor. The final piece of equipment is called the soloist. The soloist receives instructions from the PLC and executes the corresponding code to be executed by the motor. Now Vanessa will describe the HMI setup.
Hi, my name is Vanessa Yushinsky, and I will be speaking about our human-machine interface. So our human-machine interface, we used an Allen Bradley PanelView Plus 7, and that was given to us by Grove City College. So our main task that was given to us by BPMI was to mainly have a way for an operator to leave this for 7 days or more for the test to be running by itself. So next slide. So this is how we designed our HMI to have as many screens as needed, but also simplicity for the operator to use. So at first we have our setup screen where the user will put in all the parameters for the test. And then we have our run screen, which the operator will actually run the test and monitor the test as the valve is opening and closing for 10,000 cycles. And from there, we have our data screen, which basically shows past data. We have our alarm screen, which would show past alarms that have been set off, as well as different messages to help fix those alarms. And then we have an info screen in case somebody is confused on any of the functionality of the HMI. So you can go to the next screen. So this is our setup screen where the operator will put in all the values to all the parameters, mainly for the motor as well as for the PLC. We also have a valve starting position, which would mean if the valve is starting in an open position or a closed position. And all HMI screens have a digital e-stop in the upper right-hand corner of the screen. So the user can hit that at any time and that will stop the test. And they can fix the issues or see what is going wrong. As well as we have a reset parameters in case they want to easily reset all those parameters. So you can go to the next screen. So from the setup screen, they will go to the run screen, and this is where mainly everything happens. So all the parameters are set. We can start the test, and we can monitor it. So in the lower hand corner, we have our torque over time as the valve is being cycled to open and close. repeatedly. And again, it shows mainly our cycles and the pause time that it takes from switching directions. And you can go to the next screen. And at last, we have our alarm history screen, which is mainly just a very functional safety precaution. So if anything has happened in the past, an operator can come back after so many days or so many hours and see what has happened. This is where they can see past alarms and they can acknowledge them. They can basically go through them, clear them if they need to, and they will have messages to go through, basically like, okay, like if the safety cage isn't in place, like go and check that. Any of the e-stops were clicked. If the motor was over torquing or under torquing a valve, or any other system error, like if something wasn't connected, then there would be messages to help them figure out the issue and to fix that. And now I will hand it off to Daniel to talk about the PLC.
Hello, my name is Daniel Diaz, and I will be talking about the use of a programmable logic controller in our project. This component takes the user inputs from the HMI display and sends them to the Soloist motor controller. This PLC is an Allen Bradley compact logic series controller with 2 Ethernet ports, which are used to connect it to an Ethernet switch through which it communicates with the HMI and the motor controller. It has a USB port, which we used at the beginning of the project to program it, and its 750 kilobytes of user memory are more than enough for this project. The next slide shows a portion of our code. PLC program code is based on the concepts of electrical relay logic with 2 vertical racks and horizontal rungs that contain the instructions to carry out functions. Thus, it is called ladder logic. The functions of the ladder logic code for this project are as follows. The PLC receives the input information from the HMI. The operator will enter the information in the setup screen. Then it checks for safe start conditions. This means determining the state of the emergency stop buttons, the safety cage switch, the stop button on the HMI. If none of the buttons are pressed and the cage is closed, the program is clear to run. When the operator hits the start button, the PLC will send the parameters and the start signal to the motor controller for it to start the motor program to test the valve. On the next slide is the second half of the main ladder logic code for this project. As the motor program runs on the Soloist motor controller, the PLC will routinely collect the torque values calculated by the Soloist, as well as the number of cycles the valve has undergone. The HMI reads the torque information to display on a graph, and the PLC compares the actual cycle count against the desired cycle count for the test. When the actual cycle count equals the desired number of cycles for the test, the code shuts itself off and issues a command to reset all parameter values. The code can also be shut off with the reset button on the HMI. And now Micah will talk about the Soloist motor controller.
The Soloist motor controller is connected to the PLC via an Ethernet cable. It executes code and manages power going to the motor. Also, the Soloist controller can run up to 5 programs simultaneously. Our project used just 2. The first program was on task 1 and executed individual motor commands, included pause time and stop the motor. The second program ran on task 4. It ran continuously in the background and managed the transfer of variables to and from the PLC. On the next slide, the data transfer took advantage of the Soloist's ability to store data registers accessible to the PLC. One interesting problem we ran into was transferring floating points, or decimal numbers, between the PLC and the Soloist. The data registers couldn't handle floating points. So, instead of rounding and converting the floating point numbers, we took advantage of the 32-bit size of both integers and floating points. We devised a system showed here to transform floating point numbers into integers and back to floating point numbers by keeping the individual bit structure and thus preserving full precision. Now Daniel will go over completed goals.
To summarize what our sub-team was able to accomplish, despite our work on the project being suspended sooner than anticipated, we were able to control the end effector with the HMI PLC Soloist connection, specifically starting and stopping rotation of the valve actuator, oversee the motor controller with the HMI and PLC. This included initiating programs saved to the motor controller, modifying motor controller variable values, and receiving numerical information from the soloist motor controller. Lastly, from the HMI, we were able to modify PLC values, graph numerical data, and monitor programs. Next, Chris will talk about the motor actuator side of the project.
Hello, I'm Chris Wolf, and we're going to talk about the motor and actuator side of things, which is where our system comes in contact with the valve. The motor we use is the BM1400 Aerotech motor. The reason we chose this motor was as readily available to us as we were able to recycle it from the 2013 fatigue tester. We'll be using current as a means to determine the torque output, and the controller we're using is the Solus controller HPE20, and the program it uses is called AeroBasic. Next slide. Our gearbox we chose to use is the Apex Dynamics KF100 series, and what's unique about this gearbox is that it's a right angle hollow output shaft. And what this means is we're allowed to attach a shaft to the output of the gearbox, and this allows us to account for the variable heights in valves. The gear ratio we are using is 10:1, and the way the shaft connects to the gearbox is through a shrink disc. Next slide. Now for our actuator, we had to develop a valve gripper. And what this consists of, if you look at the circled disc right in front of you, this is the hand, and we had to press fit 5 fingers through the hand. And when you insert these fingers down into the valve hand wheel, and it starts to spin, it allows the valve to open and close. The fingers are shown in blue, and this is because there is a rubber tubing around it. And if the spokes around each wheel are not perfectly spaced, the rubber adjusts for that and allows us to equally distribute the forces. The way the shaft connects to the hand is through 2 external retaining clips, as well as there's an additional shear keyway, and this acts as a mechanical failsafe for the protection of our valve. Next slide. Once this was assembled, we wanted to test our system's accuracy. So we ran 5 tests at 5 different torque levels, and we compared the actual current readings that withstanded the tested torque statically and compared that to an expected current, which was calculated using a torque constant from our motor. The results showed that we were slightly over 25% error. If we had a little bit more time, we believe that the use of a torque sensor would dramatically increase our accuracy. Next slide. Now let's talk about the econ. BPMI sponsored this project and gave us a budget of $5,000. We spent $4,366.57. The motor and controller are not included in these costs and the analysis due to that we're able to recycle it from a previous senior design project. As well as the PLC and HMI were not included as well due to Grove City's mechanical engineering department purchasing that. And if you look at the sensitivity chart, you can see that the gearbox and T-slot material, as well as the stock, had the greatest effect on our budget. Next slide. In this chart, each category is organized by each expense category, and each category shows how much money we spent with respectively. Now the block dots show the cumulative percent costs, and as you can see, if you look to the top right, we spent a total of 86% of our budget. Next slide. We thank you for coming out tonight. We hope you learned a lot about our project. Are there any questions?
Great. Thank you very much, guys. We're going to follow now with questions. Again, if you have questions, just please indicate in the chat that I have a question, and I will go ahead and take all the questions in order according to that format. So we'll pause right now to wait to see if anybody has any questions.
Also, our special guests, since you don't have access to chat, go ahead and turn your mic on and ask your question.
Hello, this is Nathan Weierspan from BPMI. I have a question for the team. What was the biggest unexpected challenge you faced coming through your design? Maybe an area you thought that would be fairly easy to tackle, but turned out to be a larger challenge than anticipated?
I would say the PLC to my side of things. I can let either Daniel, Micah, or Vanessa answer that question since they're something dealt with that issue.
Before he answers that question, if I could ask the person asking the question to mute your mic.
Yeah, I can answer that. So like Mark alluded to, one of the more difficult parts of this project that were unexpected was the incorporation of the HMI PLC and the Soloist motor controller, all of which were entirely new to me, to Micah, and to Vanessa. And so on top of trying to incorporate them into the project, we were also learning the software that programmed them. So in of itself, once we got the hang of what we were doing, it wasn't that difficult, but the unexpected challenge was the learning curve, and then once we had a basic grasp of the software, coming up with a game plan for how to put everything together and make it run smoothly together. And Micah and Vanessa, feel free to chime in if you want to add more to that.
Oh, that sounds good. I totally agree. Definitely an area that we didn't know a lot about, but we know a lot more now.
Great. Thank you for the response to that question. And thank you for the question. Are there any other questions from anyone? Again, indicate in the chat if you do, or if you are a guest and don't have access to the chat, feel free to just activate your mic and ask the question.
Hi, I'm Erin Fulton, a former graduate from Grove City. I was wondering, since this is technically fatigue equipment that you would, in theory, be testing the valve in fatigue, did you consider how this equipment would sustain fatigue testing or long cycles?
I think I can answer this question. We were not able to test any of our assumptions or calculations, but we did use a mixture of just standard stress theory as well as FEA to analyze things such as the actuator hand interacting with the valve and some of the basics for the front assembly that holds onto the valve itself. So what would be acting the torque and what would be counteracting the torque, so that those had infinite life cycles or would be beefy enough to not encounter any issues that we could tell. But we were not able to validate that with testing.
Any further response for the posed question?
The V blocks were tested as well and were found sufficient at their size to last through essentially infinite cycles.
Any further follow-up?
I would just say, just one more thing. I would say that right before we were about to be sent home, we were having a program that was very close to being able to run. So we were very close to being able to actually test our rig. We were actually right on time for plans we had set with dates to be running at that time, but due to the COVID-19 outbreak, we were not able to test any of our calculations or programs fully.
Anybody care to add more? Okay, thank you. Aaron, it seemed like you had something to follow up.
Oh, I was just going to say that I thought that that would be pretty much how you should address the question. So I was happy with that answer.
Perfect. Well, thank you for your question. Any other questions for this group? Okay. Well, thank you very much. You guys did a wonderful job.